The comparatively earlier technology available since mid-1950s for secondary storage is magnetic disk. Sometimes it is also referred to as hard disk drive. Read, write, and store of data on magnetic disks happen in units that are called blocks. Blocks are contiguous sequence of bytes. Blocks are arranged in concentric rings called tracks. Each track is divided to arcs of rings, which are called sectors. Typical number of sectors per track is 500 to 1000, and typical number of bytes per sector is 512. Disks can have one or more platters that can have data on one or both sides. Platters can have 50 to 100,000 tracks per surface. Set of tracks with the same diameter are called a cylinder. A cylinder has one track per platter surface. An array of disk heads, which is also called read-write head, move together in a way that each head is on a platter. To perform the read or write operation, disks spin, arm assembly moves, and the head is positioned on the top of the desired block. Therefore, physical movements are involved in read and write in a magnetic disk. A disk controller in a magnetic disk is responsible for interfacing a disk drive with a computer. It manages commands to read and write sectors, verifying correctness, for example, by computing checksums. An important concept while working with disk is sequential access versus direct access to a location. Magnetic disks do support direct access to a desired location. However, reading and writing sequential or random or direct location have performance implications. This is due to physical movements involved in disk read and write operations in moving to a desired location. Data should be in main memory for a database management system to work with. Data is stored on disk in units of blocks. Even if only an item in a block is needed, the whole block should be transferred. The time to read or write a block depends on the location of data. Disk heads should move to be placed on the track where the block is located. That is called seek time. The smaller the size of a platter, the lower the seek time. Then the platter needs to rotate until the desired block is under the read-write head. This time is called rotational delay and is usually less than the seek time. Then there is the transfer time, which is the time to read or write, and read is usually faster. Access time is summation of three components of seek time, rotational delay, and transfer time. Flash disk or solid-state drive is a newer technology used for secondary storage. In contrast to magnetic disk, SSD does not have moving parts and works through electronic non-volatile flash memory cells. Each of these cells store a few bits. For example, 4 bits of data in each flash cell. Due to the technology used in SSD, it is resistant to physical shock. It also has lower access time and latency. SSD is gaining popularity since late 2000s as a secondary storage technology. It is manufactured in different capacities and could be specialized for I/O acceleration and needs of applications such as online transaction processing. SSDs are generally faster than magnetic disks. This is because of lack of movement requirements. The performance of SSD disk depends on the cell technology, for example, NAND or NOR-based cells, and the number of parallel flash cells used in them. Similar to magnetic disk, there is a controller for SSD which is also responsible for interfacing it with the computer. To perform data operations, data should be in main memory. Disk access is required in reading the data to main memory and in writing the committed transactions on disk. Whether magnetic disk or SSD, disk access is still a fairly slow part of disk-oriented database management systems operations. Placement of data plays an important role on disk performance. Although less difference in SSD, sequential reads and writes to closely placed data are usually faster and more efficient than read and writes on random access to data. The required physical movements in magnetic disks play an important role. In SSD, controller details and the difference in required I/O operations also affect sequential versus random access performance. Optimizing access could be achieved through scheduling algorithms. There are also data placement strategies for more sequential data access and therefore better access efficiency. Usage of redundant disks is another explored solution. This could be done for performance or reliability reasons. Database management systems also prefetch data that they might require later. This is for reducing the data transfer time between disk and memory.